Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter Coordination Compounds from Inorganic Chemistry. The previous sessions we have completed so many things up to valence bond theory we have completed. Today we are going to discuss about the crystal field theory. Valence bond theory, we said most of the points were made as assumptions and that theory unable to explain about the strength of the ligand, color of the complexes, magnetic property of the complexes, etc. Those drawbacks of VB theory can be sorted out by crystal field theory. This theory put forwarded by H. Bethe and B. Bleck. So let us find what are the important features of crystal field theory. So just to know about crystal field, it is nothing but when the metal ion is present under the influence of the electric field of the ligands. Ligands are having either a negative charge or a unshared pair of electron. So when number of ligands that surround the metal ion, what happen? The electrons of metal ion getting disturbed or affected by the electrical field of the ligands. That effect is said to be crystal field. So we can find this is the metal ion, this is surrounded by the ligand. I have taken 6 ligand about the metal ion. So this metal ion, they have their electron in its d orbital. Those d orbital electrons gets influenced by the electrons of ligands. So ligands that provide electric field about the metal ion due to the interaction of d orbital, the electrons of d orbital of the metal ion with that of the ligand. What happens? The non-spherical electric field is produced. That non-spherical electric field is termed as crystal field. So how this electric field, non-spherical electric field is formed, that can be explained for the different complexes having different coordination number. So this crystal field will be depending upon the coordination number of the metal ion. So let us find the points one by one. Here the main difference between the VB theory and CFT theory is CFT theory, it speaks about the ionic character of metal and the ligand. That means the bond formed between the metal ion and the ligand is purely ionic. But in the VB theory, we said the nature of bond between the metal ion and the ligand is purely covalent. So in this crystal field theory, the metal ion and the ligands are considered as point charges. Point charges means we are not supposed to consider its sizes and all. We are taking as point charge. So we can find the metal ion is the point about which the ligands are present. So both metal as well as ligands are taken as point charges alone. And if the ligands are carrying negative charges, then the interaction between the metal ion and the negative ligand is said to be ion-ion interaction. Or the metal ion is bonded with neutral molecules where the neutral molecules have no charge, where the interaction between metal ion and the neutral molecule is said to be ion-dipole interaction. So here the neutral ligands are referred as dipoles and in this negative ligands are referred as ions. So depends upon the nature of the ligand, the metal and the ligands can have either ion-ion interaction or ion-dipole interaction. The next one, when the metal ion is surrounded by a fixed number of the ligand, Fixed number is nothing but coordination number of the central metal ion. So based on that only, the metal and ligand can have a bond or the linkage between the metal ion and the ligand. So the presence of either negative ligand with the metal ion or the dipoles with the metal ion able to make the bond by donating the pair of electron to the metal ion. So in this case, when the free metal ion we have, free metal ion means it is not under the influence of ligand field. So these free metal ion already they have their d orbital. In this free ion, we can say all the 5 d orbitals are in degenerate position. What do you mean by degenerate? Degenerate means the 5 different orientations of d orbitals have same energy. So when these orbitals have same energy, such orbitals are said to be degenerate orbital. So metal, when it is in its free state, in the absence of ligands, they have their 5 d orbitals of same energy. These metal ions are now approached by the ligand. So ligands and the metal ion, under this influence, what happened? The degeneracy of 5 d orbital being removed, and the d orbital split up into 2 different states. Those are said to be T2g orbital and Eg orbital. So the degeneracy means they have same energy, but under the influence of ligand, what happened? The degeneracy of the orbital removed, and hence we are getting the 2 different energy states of d orbital, one with the lowering energy, the other one with higher energy. That lower and higher energies of T2g and Eg orbital depends upon the nature of polyhedra of the complex. Polyhedra means whether the complex can have octahedral geometry or the tetrahedral geometry or even square planar geometry. So in these geometries are just depending upon their coordination number. So this splitting of d orbital into 2 states is totally depending upon the coordination number of the central metal ion or and the polyhedra of the geometry. So in terms of d orbital splitting, the properties of the complexes can be explained. So in terms of the splitting of d orbital into 2 different energy states, we can able to explain about the magnetic property of the complex, geometry of the complex, as well as spectra of the complex. Okay, let us now discuss about what is the orientation of d orbital and crystal field splitting. Orientation of the d orbital, this is what studied under the shapes of d orbitals. S orbital, it is a spherical shape and it is evenly spread over all the 3 dimensions. When we talk about p orbital, the p orbital shape is a dumbbell shape and they can have the 2 lobes which are actually lying along the axis of the orbital. So in p orbital we can have the 3 sets of p orbital, those are px orbital, py orbital and pz orbital. Such a way, d orbitals have 5 orientation. Those are said to be dxy, dyz, dzx, dx square minus y square, dz square, dxy, dyz, dzx. They are grouped as T2g orbital, and dx square minus y square, dz square, that is grouped as Eg orbital. How such 2 types of orbital given for the d orbital? It is depending upon the orientation of lobes in their coordinate axis. Just to find out here, I have taken dyz orbital. In this dyz orbital, the d orbital has 4 lobes. All the 4 lobes are lying in between the axes. So when the lobes of d orbital lying in between the axes, then those are termed as T2g orbital. So all these 3 d orbital have their lobes in between of axes, and hence because of the similar pattern of the orientation of lobes, they are termed as T2g orbital. What about Eg orbital? In Eg orbital, I have dx square minus y square. It has also 4 lobes, but in this case, these 4 lobes are just along the principal axis or the coordinate axis. So you may find the difference of these two. Here the lobes are in between axes, you can find, but here the lobes are just along the axis. And in dz square also, only the 2 lobes with the circular form at the center, which is observed along the z axis. So these 2 orbital have their lobes along the principal axis and shows the similar pattern. That's why this is grouped as Eg orbital. So d orbital, it has 5 different orientation. 3 of them have similar orientation in their axis, and other 2 have similar orientation in their axis. Based on that, it is grouped as T2g and Eg. The next one, what do you mean by what I said? Degenerate orbital. When these orbital which is present in its free state, suppose the metal ion in its free state, all these 5 orbital have same energy and they are in the same position. This is what the free metal ion. In this case, all these 5 orientations are in its lower energy. Energy of the orbital is given such a way. So in the free state of metal ion, these 5d orbitals are of same energy and it is present in its lower energy state. When this metal ion is under the influence of ligand, what happens? The energy of the d orbital gets raised. You may find now the d orbital is present over here. And in this case, what happened? The metal ion being surrounded by the symmetric field of ligand. So we are getting the spherical nature of the sphere. What do you mean by spherical? We said the ion can have 2 different spheres. One is non-ionizable, the other one is ionizable. The non-ionizable is nothing but the ligands that surrounds the central metal ion. So what happens now? The ligands have their electron in its p orbital and the metal they have their electron in its d orbital. What happened? The d orbital electron and the ligand orbital electron, they get interacting. Because of the interaction between the electrons of d orbital of metal ion and the ligand, what happened? The degeneracy of the d orbital is being removed. So though they have same energy in its higher energy state, depends upon the geometry of the complex and coordination number of the central metal ion, the d orbital gets split up into T2g orbital and Eg orbital. That is what said to be crystal field splitting. That crystal field splitting is denoted by the symbol delta. If at all the splitting is observed in octahedral complexes, that will be denoted by del O. That is crystal field splitting for octahedral complexes. Or if the crystal field splitting is observed in tetrahedral complexes, that is said to be del T. And the energy gap between the T2g and the Eg orbital, that is always equal to 10 dq. In this case, we are going to discuss about the crystal field splitting in octahedral complexes and in tetrahedral complexes. Now let us discuss about the crystal field splitting taking place in octahedral complexes. So octahedral complexes usually we can represent Mn plus L6. So we can write plus or minus n, that is the charge of the complex can be plus or minus n and the metal whose oxidation state is n plus. So the octahedral complexes are actually represented such a way. In this case, the 4 of the ligands are present about the central metal ion in its equatorial plane, and 2 more ligands which are present just above and below the plane of the octahedron, and those 2 orbitals, those 2 ligands are lying axial plane. So in this case, we may find all these 6 ligands are present in 3 different coordinate axes. See that the L, one of the axial bond that lies over the z axis. The axial ligands which are just along the z axis, and 2 more ligands are along the y axis, and other 2 more ligands are along the x axis. So we know about the central metal ion, above the plane is a positive and below the plane is negative. So this side you have a plus z, this side you have minus z. Similarly, this is plus y, this is minus y, and this side you have plus x and this is minus x. Now these charges along the coordinate axis are referred as 6-point charges. So we can find about the central metal ion, the ligands are along plus x, plus y, minus y, plus z and minus z. So these central ligands, when it surrounds the central metal ion, what happened? Already we said the degeneracy of the d orbital is being removed. So the spherical nature of the metal ion is now converted into octahedral polyhedra. So here the spherical field just converted into octahedral field, but energy of the d orbital must be conserved. How it is conserved and how the d orbital is being splitted up in presence of the ligands, let us discuss now. See that in the free metal ion, all the 5 d orbital are in its degenerate state. So you can write these 5 d orbitals are in degenerate state. Now the energy of the metal ion, that is the energy of d orbital of the metal ion is raised under the influence of the spherical field of ligand. So spherical field of ligand can be represented Mn plus such a way. So in this case, this is what the ligand, it surrounds the metal ion. Only when it is surrounding the metal ion, energy of the d orbital simply raised. Now the d orbital at its higher energy state is being splitted into 2 different states of Eg and T2g. This takes place when the orbital electrons of ligand interact with the electrons of metal ion. So electrons of ligand, they have electrons in their p orbital, and the ligand electron that can be present in any of the d orbital, because we said the degeneracy of the orbital is still there, but energy of d orbital only raised. So the electron that can be anywhere of the d orbital. So when the ligand orbital approaches the d orbital of the metal ion, there only they may find repulsion. Depends upon the amount of repulsion between the ligand orbital electron and the d orbital electron, the energy of the T2g and Eg gets splitted. How it takes place? We know the T2g set of orbital have same orientation, dxy, dyz, dzx. all of them, they have their 4 lobes which are in between of the axis. When this d orbital is approached by ligand orbital, the ligand orbital, it is filled orbital, and this d orbital also can have electron in. So when this ligand orbital approaches either of dxy or dyz or dzx, you may find this is ligand orbital in which the lobes are along the axis. But in the d orbital, the lobes are in between of axes. So when they approach each other, they may find less repulsion. This is because they are differing in their orientation of lobes in their coordinate axis. So due to less repulsion between the d orbital and the ligand orbital, their orbitals of T2g gets lowered. So we are finding T2g orbital is lowered in its energy due to its less repulsion. Because of less repulsion, T2g orbital is said to be stabilized orbital. So in this case, the 3 sets of a T2g orbital is being stabilized by the ligand orbital electron. This is only because of the less repulsion between them. Now, we have to find the Eg orbital, the p orbital of ligand that can approach even the Eg orbital. Eg orbital, they have their lobes along the axis. So p orbital also along the axis. So you may find when this p orbital approaches together, what happens? This d orbital electron and the p orbital electron finds maximum repulsion. Because of maximum repulsion, the energy of the d orbital gets raised. So only the 2 of the d orbital having same pattern of orientation of their lobe that gets raised in their energy due to greater repulsion, and hence they can be in their higher energy state and T2g orbital becomes lower energy state. So because of greater repulsion, this Eg set of orbital gets destabilized. So these orbitals are destabilized by the ligand orbital. But at the same time, the energy difference between the 2 sets of d orbital is always same, and it is equal to 10 dq, and it can also be given by del O. O is nothing but for octahedral complexes. So the energy difference between these two d orbital, these 2 sets of d orbital is calculated based on their barycenter. Barycenter means at this stage only they are in equivalent energy, and the d orbital is split up into 2 different sets. One is above the barycenter, the other one below the barycenter. So the total energy state of this one equal to 10 dq. So we can say the Eg orbital is raised by the energy of 6 dq, and the T2g orbital is lowered by the energy of 4 dq. Or else we can say out of the 5 d orbital, the 3 orbitals of T2g set is lowered by minus 2 by 5 of del O, and the Eg orbital is increased by plus 3 by 5 of del O. The plus 3 by 5, it is equal to 0.6 unit, and minus 2 by 5 is equal to minus 0.4. So what we have to do? The amount of energy between them should always be equal to 10 dq. So we can write this is plus 3 by 5, this is minus 2 by 5, it is equal to 10 dq. So the plus and minus sign of these energies are given just for saying increasing energy and decreasing energy. So what do you mean by barycenter? Barycenter is nothing but the average energy of d orbital. It never change. This is what the d orbital at its higher energy state, and in this state the energy of the d orbital never change. So when you find the two different sets, by adding these two, it is always equal to the average energy of the d orbital. And moreover, how this del naught value is calculated in terms of spectroscopic method. And next one, how the energy difference of d orbital takes place. This is because it is due to the interaction of all the d orbital that do not have same amount of interaction with ligand orbital. As the lobes of d orbital, the four lobes of d orbital having different orientation in their axis, because of that only the interaction of d orbital with the p orbital is not equivalent. So this is what crystal field splitting taking place in octahedral entities. Let us discuss about crystal field splitting in tetrahedral complexes. Before understanding the splitting of d orbitals in tetrahedral complexes, first of all we should know the orientation of d orbital as well as how the ligands are present about the metal ion. We are saying tetrahedral complexes. So in the tetrahedral complexes, only two of the ligands will be on a plane, the other two ligands are out of the plane. Suppose if the complex is represented in the form of a cube, the center of the cube is occupied by the metal ion, and four of the corners of the cube are occupied by the ligands, and four more corners of the ligands are simply empty. So in this case, as the metal ion, two of the ligands are on a plane and two of the ligands are out of the plane. How such orientation takes place between the metal ion and the ligand, that can be explained on the basis of the d orbital. The center of the cube is occupied by the central metal ion, and the d orbitals of the central metal ion is just projected in the different direction of a cube. The shaded portion of the d orbitals are pointing towards the faces of the cube. Those are designated as e orbitals, while unshaded portion of the d orbitals which are pointing towards the center of the edges, as they show difference in their pointing, we can able to calculate the angle between the metal ion and the ligand. So out of two orbital in the E set, the tetrahedral angle is 109 degree 28 minutes. In this, the orbital which are pointing towards the faces, we have two orbital. Out of one orbital can have the angle of 54 degree 44 minutes between the metal and the ligand. If we take about the T2 orbital, three of them we have, so we can find out what is the angle between metal and the T2 orbital. So 1 by 3 into 109 degree 28 minutes, that makes 35 degree 16 minutes. This calculation which helps us to find the orientation or the interaction of p orbital of ligand and the d orbital of metal ion. So by comparing the angle between the metal and the ligand, we may find the T2 orbitals with the metal ion finding the lowest angle compared to E orbital with the metal ion. So as this angle is very lower, what happened? The ligands very close to the T2 orbital rather E orbital. But the E orbitals having the higher energy away from the ligand orbital, hence experiences less repulsion, therefore lowered in energy. So based on this calculation, we can write the crystal field splitting in tetrahedral complexes. So these 5 orbitals of degeneracy is finding in metal free ion. So in the approach of the spherical field of the ligand, the energy of the free ion gets raised, and when there is interaction between the ligand orbital electron and the metal electron, the d orbital split up into two sets where the T2 orbital is raised and E orbital is lowered. So in this case, the E orbital, which is lowering by the energy of minus 6 dq, or we can say minus 3 by 5 of del T, that is T for tetrahedral complexes, and the T2 set of orbital, they are increased by the energy of plus 4 dq, or we can say plus 2 by 5 of del T, and this barycenter, the energy gap between the T2 and E orbital is always equal to 10 dq. Now let us find how the energy required for the tetrahedral complexes, whether it is greater or lower than octahedral complexes. Actually, tetrahedral complexes, they are lowering in energy compared to octahedral complexes. This is why, because in the octahedral complexes we are using 6 ligands, but in the tetrahedral complexes we have only 4 ligands. So you can find the ligand field of tetrahedral complexes is only 2 by 3. That means we can write 4 by 6, 4 for tetrahedral complexes, 6 for octahedral complexes. You can solve it, you are finding only 2 by 3. So the ligand field of tetrahedral complexes is decreased by the factor of 2 by 3. And one more point, we can say the direction of ligand orbital towards the d orbital. In the octahedral complexes, the ligands are approaching towards the d orbital of metal ion. But in the tetrahedral complexes, as the lobes of the d orbital pointing towards the faces or pointing towards the edges, none of the d orbital is close to ligand orbital, and hence the direction of ligand field is not coincide with d orbital. Therefore there also it decreased by the unit of 2 by 3. So by taking 2 by 3 into 2 by 3, then the energy of tetrahedral complexes is lowered by 4 by 9 of octahedral complexes. So the decrease in energy of tetrahedral complexes is calculated depends upon the ligand field of the complexes and the direction of ligand field towards the d orbital. So in the tetrahedral complexes, the E orbitals are stabilized and the T2 orbitals are destabilized. And moreover, as the energy required for the tetrahedral complexes is much lower compared to octahedral complexes. All the tetrahedral complexes are found to be high spin complexes because the pairing of electron does not take place, since the crystal field splitting energy for the tetrahedral complexes is lowered by the unit of 4 by 9. Therefore, most of all the tetrahedral complexes are found to be high spin complexes. That's all the crystal field splitting taking place in tetrahedral complexes. Okay students, let us close our today's session. Today we have discussed only about crystal field theory. In this theory we just discussed about the crystal field splitting of octahedral complexes and tetrahedral complexes. Okay students, let us close our today's session and we will continue the same chapter in our following sessions. Until then, bye bye.